Hi, my name is Jan-Philipp Göpfert, and I'm going to tell you about adversarial robustness with respect to different LP norms. Before we begin, let me introduce the people who worked on the content I'm going to present. First of all, there is Niklas Risse, a brilliant student currently finishing his master's at Bielefeld University, who has done all the heavy lifting involved in this work. Then there is Christina Göpfert, as well as myself, Jan-Philipp Göpfert. We are both PhD candidates in the machine learning lab led by Barbara Hammer at Bielefeld University, and know us sharing a surname is not a coincidence. On to some motivation, where I will explain what adversarial attacks are and why we concern ourselves with them. Take image classification as an example. You have a state-of-the-art deep convolutional neural network, and when you hand it an image, it'll tell you its predicted label. For example, dog or duck. Or sometimes it'll get things wrong, snake when it should say lizard. Now, for a variety of reasons, we want to know how the model reaches its conclusions. This might be because we are concerned about fairness or generally biases contained in the model, or because we can be legally required to explain predictions, or simply because we want to figure out how to improve the model. And this is especially interesting when we see the model making a mistake, as above with the lizard. Let us think about how images are classified. Here's a photo of a cat, and if you ask me why I say that it's a cat, I might point out its ears or its eyes. You know, whatever I see in the photo that maps to something in my understanding of the world which points to cat. I have a lot of background information available, and I can reason about what I see and why this is a cat and not a dog, and so on and so on. Now, by its very nature, a convolutional neural network perceives the image very differently. There are certain configurations of pixel values that come together and eventually lead to the prediction of the model. You could say that this process is, by comparison, very straightforward, but at the same time it is difficult for us to grasp what exactly is going on. What I think is important here is to realize that there is an inherent disconnect between how machines perceive images and how we as humans perceive visually. But in both cases, you can try to understand a prediction by asking what would need to change in the image for a different prediction. This required change we call a perturbation. Because of that disconnect in perception, one can find a perturbation that does not change the semantics with respect to human perception at all, but which makes a huge difference to the trained model. When you find and apply such a perturbation, you're essentially breaking the model, and so this process is referred to as an adversarial attack. Obviously, a model breaking is problematic, and so we talk about adversarial robustness as a property of a model that determines how large such perturbations need to be in order to have the desired effect. Essentially, more robust means that larger perturbations are required. When you have a model that is adversarially attacked, of course you want to defend it, and that means making it more adversarially robust. Several techniques that in large margins have been proposed, and they all effectively change the model such that larger perturbations are required to attack the model. Before we move on to the actual new content, let me briefly mention that it is debatable how relevant adversarial attacks are in the real world. People bring up traffic signs and that they can be tampered with, and there is super exciting work around this. However, I think that this disconnect between human and machine perception is extremely exciting by itself, and by understanding it better, we can increase our knowledge of machine learning in general. So, onto our problem. Say you have two models. Both have been trained such that they are adversarially robust. One is robust up to perturbations with a Euclidean norm of 0.5, and the other one against perturbations with an infinity norm of 0.2. Which one's better? How can we decide? Apart from these different values, which norm is the right choice? To approach these issues, we make use of adversarial robustness curves. These allow us to look at not just an individual perturbation size, which, by the way, are commonly called epsilon. On the previous slide they were 0.5 and 0.2. Instead, we consider all possible values that epsilon could reasonably take on. I mentioned that the perturbation size required to change a prediction for a given point x is the distance to its closest decision boundary. So, for any epsilon, we consider the points that lie within an epsilon of a decision boundary. In this equation, d denotes the distance function. Also, this is slightly simplified and lacks normalization, but you hopefully get the idea. Let us just look at an example. On the left, we see a binary classification problem. The decision boundary is the black line, and to either side there are points from different classes, red and blue. By construction, all these points are the same Euclidean distance from the decision boundary, exactly 1. This means that to change their predictions, you have to move them by at least that much. In the right plot, we see this in the red robustness curve for the L2 norm. Below 1, not a single point can be adversarially attacked, and above 1, all points can be attacked. Because the classifier is nonlinear, though, for the L1 norm and the infinity norm, we get a very different picture. That was just to give you an idea of what an adversarial robustness curve might look like. Let us look at real data and proper trained classifiers. What we see here are robustness curves for classifiers trained on 4 different data sets: MNIST, Fashion MNIST, German traffic signs, and CFAR10. The infinity norm is very convenient here, because even though the images are of different sizes, they have been normalized in the same way, and the largest sensible epsilon is 1. Let's compare the 2 extreme cases, CFAR10 and MNIST. CFAR10 is the leftmost yellow line. It reaches the top even below an epsilon of 0.2. This means that one can change the prediction for every last point with a perturbation smaller than 0.2 in the infinity norm. In contrast, for MNIST, the rightmost red line, at an epsilon of 0.2, one can only successfully attack around 10% of all points. So here we can already see one of our main points. Being 0.2 robust in the infinity norm can mean wildly different things in different cases. Now, where do these differences come from? By just considering the distances between the points in a dataset, we can already get an idea of its scale. In the right plot, you can see that the points in CFAR10, which is now the turquoise line, are far closer to one another than for MNIST, which is now the blue line on the right. It makes sense that when there is not as much wiggle room between points to place decision boundaries, it is more difficult to achieve large margins. Finally, let us look at a couple of adversarial examples. In the left column is the original image that is attacked. It is the same image 3 times. In the other 3 columns, we see the results of adversarial attacks that minimize our 3 favorite LP norms. And the 3 rows stem from 3 different models. The one for the top row is a common model trained without adversarial robustness in mind, and the other 2 are hardened models, one against L infinity norm attacks and the other against Euclidean norm attacks. What is especially noteworthy here is that for the hardened models, the perturbations are more clearly focused on the semantically most relevant area in the middle. Alright, just 3 points for you to take home with you. First, global robustness provides more information than a single epsilon. 2, different norms are important. And 3, scale is also very important. I thank you for listening, and I hope you enjoyed our work.